So let's touch firstly on interference. Remember, there are two types of interference. There's either constructive interference or destructive interference. Now, constructive interference, you'll remember, is when two or more waves come in and their amplitudes combine. And the resulting amplitude is greater than that of either of the individual waves, and we simply add the two together. Oppositely, with destructive interference, the amplitude of the resultant wave, once we've added two or more waves together, is less than the individual waves. So then they're cancelling out. All interference associated with light waves occurs when the electromagnetic radiation or the electromagnetic parts of those waves combine. So there's a couple of conditions for interference that must be met if we are to observe interference in light waves. These are, the first is that the sources must be coherent. So we must have at least two sources and the light must be coherent. And when we say coherent, that means that they must maintain a constant phase with respect to each other. That doesn't mean they necessarily have to have the same phase. The phase difference between them cannot be changing. Secondly, the sources must be what we call monochromatic. Monochromatic means that they both have the same wavelength. So you might be wondering, how do we produce coherent sources? How do we have two sources of light and ensure that they have the same phase difference? Because getting the same wavelength seems quite simple, but what about having the same phase? Well, actually the easiest way to do this, and really quite a clever way to do it, is to illuminate or to light up a barrier. Now the barrier is going to contain at least two narrow slits. Now, since there's one single light source that is illuminating both of these slits, the light that is passing through those slits is coherent. So these two slits are going to act as two different sources, and we can say that they are coherent. And they're obviously monochromatic as well because they're from the same light source. The next obvious question is, what happens when the light passes through those slits? Now remember, when we were doing our ray approximation, we assumed that the width of the slit was significantly larger than the wavelength of light. Not the case here. The slit width is actually on the order of the wavelength of the light, which means we're going to see some really interesting things happen. Now, light passing through very narrow slits does a thing that we call it diffracts. So it diffracts and it sort of fans out when it passes through those slits. So plane wavefronts that were approaching two different slits are then going to fan out. So you can think of it like Huygens, remember back to Huygens' principle, how along a plane wavefront, Huygens proposed that there were individual point sources along those wavefronts. Well, if you're approaching a narrow slit, you're only going to have, say, one of those point sources pass through the slits. And because they're point sources, remember, they're going to radiate out spherically. So then you're going to end up with this spherical fanning out or radiation that's passing through the slits. And this is what we call diffraction. Now, the amount that the light actually bends once it passes through a slit is dependent upon the slit width. So remember, for something that's really quite, for a slit that's really quite large, the light's just going to pass through there. As we start narrowing it down, the light is going to start diffracting out more until it becomes really narrow, and then you get more and more diffraction. So remember, smaller slit width equals more diffraction.